in the last segment we discussed about the variation of strain across a cross section under pure bending, and we figured out that the relationship was in x direction. Strain in x is nothing but negative of y over c times maximum shear maximum stress that occurs at any fiber. So this is where we had stopped, and yeah, if just to remind you, so this is the configuration and y is the distance from the origin. Okay. Now we are set to derive the relationship between the stress that how it varies with respect to distance across the cross section. But not only that, there is one more thing. See, here we are using the maximum stress as a factor and defining everything in terms of that. This does not tell anything about how it is related to the applied external loading. That is very important to know, because that is what we always want to know, that if I apply a particular amount of moment, what will be the stresses, what will be the strains that are developed. So, if you remember the torsional theory, we followed the same steps. We first derived a relationship like this with respect to the maximum strain, and then using the equations of equilibrium we figured out what is the distribution of actual stress with respect to the applied loading. So, the same steps we will follow here, and under the assumption that all the strains are very small and the materials are still under the yield point limit. So, that means everything is linear, and that is how, if I just multiply the elasticity modulus, say for example E here and E here, okay. So, this will give me the stress values, because stress and strains are proportional now under the limit of yield point. So, I can just write that sigma of x is negative of y over c sigma of m. Now, this tells us that the stress varies across the cross section, any cross section for that matter, in this way. So, just to show a diagram, suppose this is the side view of the beam, and this is the side view of the cross section at which we are discussing these things. So, then anywhere we do not know yet, suppose this is the slightly above, shall I draw so that it will be clear. Suppose this is the neutral axis at which there is no strain whatsoever, neither compressive nor tensile, then this tells us that wherever, suppose here the maximum stress is happening, and then we define our axis like, so this is your positive axis, x axis, this is y axis, z is coming out. Now, if you see this, it is telling that at y is equal to 0, sigma x is 0. So, that means sigma x is 0 at y is 0, but when y is positive c, suppose this distance is c, right. So, the maximum distance from the neutral axis, if that is c, then at that point it is minus sigma m, which is something like, say, like this, and it varies linearly. So, this can be represented like this, and this value is minus sigma m, maximum value. And if we go the other direction, that is negative y, we will get a positive sigma. So here we are plotting the sigma versus y, okay. So this direction we are plotting sigma. And then is that so? Yeah, So now if we go below the neutral axis, y will be negative and it will be positive number and it will be some fraction of that maximum, but it's again is linear up to this point and something like this. Okay. So that is how the distribution of stress, and the same distribution for strain also, they are proportional, just a factor of E between them. But still it is not clear where this neutral axis is. We have said that suppose the neutral axis is there, then the distribution happens to be this. But we have no idea where this neutral axis is, and we have no idea what this sigma m will be for a given moment for a given cross section. So that is what we are going to now figure out. And those things we will figure out by using the equations of force equilibrium. Now what do I mean by that is, go to the next slide. Suppose we have a section, a representative section like this. Okay, so this is the cross section of the beam, and we said that there will always be a plane of symmetry, and our moment is acting on that plane of symmetry. Now there are some facts about the stresses which I would like to point out here. The first one is the integral of the sigma x over the full area of cross section is 0. Now what does it mean? It means that, see, or in this previous case, let me draw it here again. If there is a beam in our canonical configuration, we had moments being applied here, okay, m and m, but there was no axial force that was acting. Now because there was no axial force acting, that means in this way F was 0, okay, so they were 0, so there will be no force whatsoever in this direction, okay. So now I'll draw even the axis directions. Suppose here is your neutral axis, this is your z direction, this is your y direction, and x is coming out. If you compare with this picture, x was in this direction, y was this, and z was coming out. Now we are looking at the cross section from this direction, so this looks like that, okay. Now if we consider any area for say suppose here it's dA, now we are increasing the stress sigma x which is coming out of the plane or going inside the plane if it is compressive. Now if we sum them up, then it has to be 0 because there is no external force or external load that is coming in this particular direction, in the x direction. So this is basically the force balance in the x direction. And then similarly, another point is this. If we take moment about this y axis of all the stress, that will give me something like this. So z times sigma x dA, okay. And then just one point I want to make clear, that even in these equations now we are not telling anything very specific about what the form of sigma x is, okay. Sigma x, how it varies across cross section, we don't have exact definition yet. I mean, we derived it, but in writing those equations, so this is the variation of with respect to y, but given sigma m. But here in writing these things, we are not even thinking about that expression. We are just saying that the force balance, whatever this sigma x is, the balance will be there. And if I integrate this over the full cross section, this also has to go to 0 because This just tells me that this y axis is a plane of symmetry, and because our this stress field is symmetric about y. Okay. And beyond that it does not tell anything, and this is true, this ought to be true, because see, our loading is symmetric. That means we are applying the moment on this plane of symmetry, and geometry is symmetry. So then there is no reason why the stress field which gets developed from this will be unsymmetric. So that is why about this y axis there is no moment which is also acting about that. So that will be 0, and it tells me that the stress field which it matches the intuition, the equation, everything matches, that the stress field has to be symmetric because of plane of symmetry is there. So this tells me that. So this gives me not much information beyond which we already had known from the symmetry of the problem. But the third equation will give us more information like this, and that is if I take the moment about the z axis, and that will give me like minus y times sigma x dA is the applied moment m over A, sorry, over the area A. Now this I'll just talk a bit about this minus sign. See, this is there for a convention that this moment which we are applying that makes the beam concave upward, that is positive. So that's a convention that this moment is positive. Now when that is positive, if you see here, when we go up in this axis in positive y, now sigma x is negative there because it is compressive. Now that negative sign in sigma x cancels out this negative sign, and we are getting a positive moment. So if I draw again, or can I show it here? Yeah, or else I'll do it here again. So like this is the thing, and you have this distribution maybe, so like that. Okay. If I am at a particular location from say this axis, so suppose I am here at a distance y in this positive direction, sigma x is negative, so that negative cancels out this, and I am getting a clockwise counterclockwise moment, and that matches with this direction of this moment, right? And similarly, if I come to negative y, sigma x is now positive, but this negative y cancels out this negative sign, and it again still we are getting this clockwise positive sense. Okay. So that is why this negative sign sits here to make our convention proper, and that's it. So these are the three basic force balance equation which have to be satisfied if the thing is in equilibrium. Now we will use them this and this primarily, because this does not give us any more information than saying that things are symmetric about the y plane. Okay. Now we will one by one we will use this equation to get some more information, because primarily if you remember, we do not have two information. One is where the neutral axis is and how the stress or the maximum stress is related to the moment that we are applying. So these are the two questions which will be answered by these two equations, along with this variation which we have derived now. Okay. So let us use that. So our first equation is telling us that it is sigma x times dA is 0 over the full area, and at the same time we know that sigma x is nothing but negative of y over c times sigma m. Now just substitute this here. So that will give us negative sigma m over c. These are constants, I have brought them out. Integral of y dA 0 over the area. Okay. So that means the force equilibrium equation with the variation of stress information is telling us that this equation must be satisfied. Now for a given moment, definitely there will be some sigma m. So this term cannot be 0. So that means this term has to be 0. Now that means that's the conclusion we are getting, that is integral of y dA is 0. Now this tells us that the neutral axis passes through the centroid of the cross section. Now why does it tell it? Why these two sentences are equivalent? See this. Earlier we had assumed that our neutral axis passes through some point. We didn't know which point it passes through. So this neutral axis or neutral surface you can say, because this is a complete surface, this passes through some point on the cross section. We didn't know where it is, but and then we had defined our origin of the coordinate system at that location, wherever it was. And then with respect to that origin of the coordinate system, we are getting this information. Now think about the definition of centroid. For a given cross section, suppose you have a given cross section like this, or just arbitrary, no? Why this? I have some area like this, and I have some coordinate like that, say x and y. And how do I find out the y coordinate of my center of gravity, or if gravity is constant, the center of gravity and center of area will be same. So how do I find out that? So what I do is I take an area, say dA, then I take this distance y of that area, then I do y times dA and I integrate over the full area, divide by the full A, is what I get is y center of mass, right. So that is what I get. But then what happens if by chance or by some means or some intuition I had chosen my the origin of my coordinate to be at the center of mass. For example, suppose the center of mass is after this calculation, it suppose comes out to be this point. Okay, suppose this is the center of mass. Now, so that means this one is my YCM, and then suppose by chance I had taken my origin here, then definitely I would have got this to be 0, right? And that is precisely what I am getting here. That means I am getting this term 0. So now you trace it back, this argument, in the opposite direction, so that if this is 0, that means by chance the origin that I had chosen is coinciding with my center of gravity or center of mass or center of area or centroid, right. So that's the meaning of this sentence, that the neutral axis passes through the centroid of the cross section. So the first equation gives us the complete information about the centroid. Once we know the cross section, we know where it passes through. Then let's go and discuss the second equation, that means the third one. This tells us that, what did it tell? Say this one. So negative y times this is m. Okay, so negative of y times sigma x dA is m. Now again we have the same variation of sigma x is nothing but negative of y over c sigma m. So just substitute it here to get the equation. That this negative things cancels out. I'll get, say, sigma m over c, then integral of y squared dA is equal to m, right? So here again this term you should be aware of, that this is like the moment of inertia about what? About the z axis, in fact. Okay, if you see this picture you can realize yeah. So the z axis, if it is coming out like this, so about that you are taking the moment of inertia, because y times area. Okay, so that's what is this. Where did I write that? Next one. Yeah, so then we can simply write here that sigma m I over c is m, but generally it's written like this, like sigma m is nothing but mc over I. So it's very important equation. Just see that it intuitively it makes all sense. It tells you that if you keep everything constant, that means the same beam you have, but you increase the moment on that, so obviously the stress which is occurring at the maximum or the farthest fiber from neutral axis. Now you know where the neutral axis is, so now you can know which is the farthest fiber from the neutral axis. At that fiber the stress will increase as you increase the moment, right? And similarly, if you keep other things constant, the moment is same, the moment of inertia is same, and then you are thinking about in which fiber the stress is maximum. So that fiber which is farthest from the neutral axis, the distance c, if somehow if you can increase that distance, then or decrease that distance, then sigma m can be reduced, and if by some chance it increases the c by keeping all the other things constant, then your sigma m will increase. And similarly the moment of inertia, this moment of inertia is like a resistance to your stress, developed stress. That means if you increase this moment of inertia, the stress developed will be reduced for the same moment that you have applied for the same farthest fiber. Okay, so that's what is the equation is telling you, and from here in fact you can write down the general equation, that sigma x now varies like what it will be yeah, minus m y by I, sorry, right, because this c will be replaced. So that means using this equation, yeah, this equation and the value of sigma m now we have got. So this is what we get, because if you just eliminate sigma m from those two equations, you get this. Okay, so that's fine. So now we know complete information about what is the stress that gets developed once we apply a particular moment m on a given cross section of a given type. Okay, so that's very important. And one important point you have to be very careful about, or it's a comparison between the moment of inertia which you use in torsion and the moment of inertia that you use in bending. See, in torsion you use the moment of inertia which was so suppose this was the surface. Okay, so suppose this is the surface, and your moment of inertia you calculated was about this point, this axis, okay, so that it gave you a resistance about the torque that you apply. So, the more this moment of inertia of this cross section about this axis, whatever axis this is, suppose this is x, about this, it gave you that resistance. But now, if you see the present condition of bending, here we have a case like this, something like that. So, maybe yeah, so this is the beam, and here now your axis of consideration is this, and this passes through the CG. Okay, this is the z axis according to our convention. So, let me draw even the, so this is x, so this is y, and this is z. Okay. So, here it was x, and y and z can be any direction, okay, y in this and z. Yeah. So, about this and the cross sectional area which you are concentrating is this, right. So, now you are and then I will draw the even the moment to which it tries to resist. Now, you are applying the moment about this z axis, right. So, it in this way, this is the moment that you are applying about the z axis. That is why that is the cross sectional, or the that moment of inertia, that is the in plane moment of inertia, which is causing or responsible for this resistance to this moment. And similarly, this perpendicular moment of inertia is responsible for providing the resistance to torsion. Now, here I just remember one thing. Here you just see, note here one point, that this part or portion of the equation which deals only with the cross sectional property, the moment of inertia and the farthest fiber's distance. Other thing is just the external load. Now, this term has been given a name called section modulus, okay, section modulus. Okay. Now, so what is that? It's like this, you know. So, sigma m you can write as m over s, the section modulus. That means any modulus for that matter is like efforts per effect, right. For example, your stiffness is a modulus of a spring. So, force per unit extension. Similarly, Young's modulus, stress, effort per strain, the effect. So, here if you want to define S in that way, so S will be a moment that you apply for per unit maximum fiber stress that you develop under bending, under pure bending. So, that is how it is a property of the cross section which directly tells us how effective some cross section is against bending. So, we will discuss a lot about these properties in the coming segment. See you in the next segment.